Today we are learning Euler's method. Euler's method is named for the very famous mathematician Leonhard Euler. He was a Swiss-German mathematician. Swiss-German, so it's pronounced Euler, not Euler. We like to pronounce names correctly when we can. All right, Euler's method. Euler's method is what is called a numerical method. It's a numerical method for approximating values of a function. I'm going to show you visually what the process is. Let's say that we know one point on a function. We know a point on the function. And we don't know any other point on the function. All we know is that one point. Let's call it AB. So this is where x is equal to A and y is equal to b. All right. We also know a way, they give us information to find the slope of the tangent line at that point. And if we know the slope of the tangent line, we could write the equation of the line going through that point. Let's say that the slope of the tangent line right there is 1/4. If we know that the slope of the tangent line is 1/4, then the tangent line is probably going to look something like that. Yeah? That might be a little bit too steep, but you get the idea. So on this line, we can find points on the line. And points on this line would approximate points on the curve that we don't know. Points on the line would approximate values of this function. So if this is the tangent line, then the actual curve must be something a little bit along those lines, like it has that slope of 1/4, so something along those lines. So you see that this point approximates these points. All right? And then that would just be, this is a visual for a tangent line approximation. Euler's method takes it steps further. So with Euler's method, you can then find the slope of the tangent line at that point. So again, you're given information about how to find the slope of a tangent line. If we know that let's say that they give us that the slope of the tangent line there is 2. Well, if the slope of the tangent line there is 2, then again we can draw a tangent line, and the tangent line would look like that, right? So again, we can find points on this curve that are going to approximate values of the function. So that would tell me that clearly the curve does not look like this. The curve probably looks like that, and then it gets steeper. After this point, it gets steeper. Something like that. Alrighty. So tangent lines, repeated tangent lines, help us to find points on the curve. Approximate points on the curve. They are approximately points on the curve. So Euler's method is a way to approximate points on a curve. So Euler's method approximates points on a curve, on a function. All right? All right. So Euler's method is most useful when our differential equation is not separable. Okay? There are many, many differential equations that are not separable. Some of them we learn techniques to solve in differential equations. But even so, there are still going to be some types of some differential equations that we just cannot solve. So if we cannot solve them in any way, Euler's method becomes a very useful method for finding out what the curve looks like. As do slope fields. Slope fields also give us a great information about what curves look like. Okay? So Euler's method uses tangent lines, which means we are using point-slope form of the equation of a line. So point and slope. Today is going to be all about point and slope, and it's repeated, point and slope. Okay? Alrighty, first of all, if you are watching this in 2025 or before, then I just made new example problems. So these example problems are not going to match yours exactly. So you can make the changes where appropriate. For example, in number 1, your number 1 looks very similar to this, except there's only a 2 here, not a 2y. So go ahead and change it to 2y right now on your notes packet if you are watching this in 2025. Okay? Alrighty. So let y equals f of x be the solution to this differential equation. The point 0,5 is on the graph of f. Use Euler's method with 2 steps of equal size, beginning at the point 0,5, so that's our starting point, to approximate f of 0.8. We're going to treat this like an FRQ. We're going to practice multiplying with decimals. Since Euler's method is a numerical method, you can expect it to have messy numbers in it. So let's practice our decimals and our fractions and remind ourselves how to multiply, add, subtract decimals. Alrighty, so we begin. We are going to start at the point 0,5. So 0,5 is our starting point. Then we're going to take 2 steps. So after the first step, we will be at another point. Then we're going to use this point and do a second step till we get to our ending point. And our ending point is going to have x coordinate 0.8. Since these are 2 equal steps, from 0 to 0.8, the x coordinate here must be half of this difference. So the x coordinate here has to be a 0.4. Okay? Several years ago, a student wrote this on her paper for Euler's method problems, and I liked it so much that that's how I teach it now. I like that visual. So our answer, you guys, is right here. This y coordinate is our answer. All right, and now we start our steps. And it's tangent line approximations, so it's point and slope. So we're going to do point and slope, then EQ, and then we're going to find our approximation. Okay? One step, and we will have something very similar over here. We will have something identical over here. Alrighty, the first point that we have is 0,5. The slope. They gave us information about the slope right here. So this is the slope equation. They gave us an equation to find any slope given any point, right? We want to find the slope at that point. So we are finding the slope at the point 0,5. So I'm putting 0 in for x and 5 in for y. 0 in for x, 5 in for y. So this is going to be 0 minus 2 times 5, which is negative 10. So the slope at that point is negative 10. Our equation, y minus the y coordinate of the point, is equal to the slope times x minus the x coordinate of the point. That's our equation. And now we go to our approximation. The approximation, we are approximating f at 0.4. So we are going to put 0.4 in for x. We'll be putting 0.4 right there and solving for y. So I'm going to add 5 to the other side and put 0.4 in for x. This is going to give us 5 minus 10 times 0.4. 10 times 0.4 moves the decimal point over once, and we get 5 minus 4, which is 1. So we found our first y value, 1. Should have put a little line right there. Okay. Now we have a new point, so we repeat the process. Point slope, EQ, approximation. The new point is 0.4, 1. The new slope is dy dx at our new point. So we are putting 0.4 in for x and 1 in for y. So that's going to be 0.4 minus 2 times 1. 0.4 minus 2 is a negative 1.6. That's our slope at that point. So now we find the equation. Y minus the y coordinate of our point is equal to the slope times x minus the x coordinate of our point. And now for the approximation. We are approximating f at 0.8. That's our y value. Add 1 to the other side and replace x with 0.8. We're going to have 1 minus 1.6 times 0.4. Okay, a little decimal multiplication review. I need to multiply 1.6 times 0.4. Oops, I'm off screen. 1.6 times 0.4. So let's review how to multiply with decimals. I multiply as always I'm ignoring the decimals at first. So 4 times 6 is 24, carry the 2. 4 times 1 is 4, plus 2 is 6. So 16 times 4 is 64. Now we deal with the decimals. There's 1 decimal from the 1.6. There's 1 decimal from the 0.4. So that makes 2 decimal places. So I move my decimal 2 places to the left. So 1.6 times 0.4 is 0.64. So we have 1 minus 0.64, which is 0.36. So f of 0.8 is approximately equal to 0.36. Multiple choice answer. If it was not multiple choice, I would have say stopped a little while ago. I'm going to shut this door. Keep some external noise out of the room. Okay. Alrighty, on to the next one. This next problem is identical to the one from 2025, so you shouldn't have to change a thing for this one, you guys. Alrighty. There's our slope equation. They gave us our slope equation. And f is the particular solution, where f of 4 is negative 1. Use Euler's method starting at x equals 4. So we're starting at the point 4, negative 1, with 2 steps of equal size to approximate f of 4.2. So we are starting at 4, negative 1. We're going to take 2 steps again. So we're going to go 1 point and then another point. And when we end, the x coordinate should be 4.2. So I ask myself, what x coordinate is halfway between these two x coordinates? And that would be 4.1. So I'm going to get a y value here. That'll be my first step. And then I'm going to get a y value here. That will be my answer. So our answer is right there. And I just realized I never did put the answer up here, so I might as well do that. That would have been 0.36 over there. FYI. Okay? Alrighty. Euler's method. Point, slope, EQ. Approximation. Point, slope, EQ, approximation. That's one step. Then we'll have the same steps over here, or the same things over here for our second step. Okay, first point is 4, negative 1. First slope. is dy dx at that point. So you can write dy dx equals, or you can just go write 4 plus negative 1. You don't have to say dy dx equals. The slope at that point is 3. Now for our EQ, y minus the y coordinate of the point is equal to the slope times x minus the x coordinate of our point. Now the approximation, we're approximating f at 4.1, so f at 4.1 is approximately equal to, I'm looking above there, and I realize I did not put approximately equal to here. Those should have been really approximately equal to's. Sorry about that. I did better when I made my notes that I posted, but okay. This is just an approximation. Alrighty. So I'm subtracting 1 to the other side, and then replacing x with 4.1. And again, I'm treating this like an MCQ, so I'm going to go ahead and have fun with decimals here. This is 3 times 0.1. 3 times 0.1 is 0.3. Negative 1 plus 0.3 is a negative 0.7. So our first y value here is negative 0.7. And now we're going to do the same steps on the other side. Okay, had to take a brief bunny break. Alrighty, point and slope, and then EQ. Lastly, the approximation. Alright, our point. Our new point is 4.1, negative 0.7. Our new slope, we're using our slope equation, so it'll be 4.1 plus a negative 0.7. 4.1 minus 0.7, 3.4. Yeah? Okay, so our equation, y minus the y coordinate of our point is equal to our slope times x minus the x coordinate of our point. Lastly, the approximation. We are approximating f at 4.2, so we're going to put 4.2 in for x. I subtract the 0.7 to the other side. I'm putting 4.2 in for x. And so I have 0.7 plus 3.4 times 0.1. So 0.7 plus 0.34, and I'm thinking I made a mistake with my signs here for some reason, you guys. Okay, I just saw it. When I moved this 0.7 to the left, or to the right, I should have made it negative there. So this is a negative 0.7. Alrighty. So we have negative 0.7 plus 0.34. So you can either do that mentally or come off to the side, and we are actually subtracting. We're subtracting these values. It's actually negative 70 or negative 0.7, but we're subtracting the absolute values of them. So this is going to be 0.36, right? So this is going to be a negative 0.36. So that is our final answer, negative 0.36. That is our approximation, and we don't have to rewrite it here. Our approximation, f of 4.2, is approximately equal to negative 0.36. Multiple choice answer. Because if it was FRQ, I would definitely not have dealt with decimals. Definitely. All right, next example. This next example is very similar to the one that I made in 2025. I just added more values, all right? But I kept the important values the same as what I had in my example for 2025. So you shouldn't, if you're in 2025, you shouldn't have to add or change anything. But if you want to add this, if you want to change it up, go right ahead. Let f be a differentiable function. Values of f and f prime are given for selected values of x in the table. Use Euler's method with two steps of equal size. I'm going to get rid of this. So 2 steps of equal size, all right? Beginning at the point when x is 3. We're beginning at the point when x is 3 to approximate the value of f of 2.6. So we are starting at the point when x is 3. So we're starting at the point 3 what? I go to my table when x is 3, f is 2. So we are starting at the point 3, 2. And we're taking 2 equal steps to get to the point when x is 2.6. So we're going to go through one point and another point because it's 2 steps, and we're ending when x is 2.6. I know that this y value will be my answer. So I'm asking myself, what x coordinate is halfway between these two x coordinates? And 2.8 is halfway between those two x coordinates. So that goes there. So this table gives extra information that we do not need. All right? Okie-doke. Euler's method. Point and slope. Then EQ. And lastly, the approximation. Our first point is 3, 2. Our first slope is the slope at x equals 3. And at x equals 3, the derivative is 0.4. So f prime at 3 is 0.4. The equation, y minus the y-coordinate of the point is equal to the slope times x minus the x-coordinate of the point. Therefore, our approximation for f of 2.8 is, we add 2 to the other side, plus 0.4 times, and I'm replacing x with 2.8. So I'm going to be careful here with my signs. We have 0.4 times negative 0.2. So I need 0.4 times negative 0.2. So I multiply as if the decimals are not there, and I get 8. But then I have 2 decimal places. So it's going to be 0.08, 2 decimal places. And then we have 2 minus 0.08, which is 1.92. That is our the y-coordinate of our middle point. And now we use that middle point and do it one more time. So point and slope, and then EQ. Lastly, the approximation. Every Euler's method problem. The point is 2.8, 1.92. The slope is y prime at 2.8. Sorry, off the screen. The slope is y prime at 2.8. So the slope is f prime at 2.8. That's going to be the 0.7. So there's a lot of information in that table that we don't use. Y minus the y-coordinate of our point is equal to the slope times x minus the x-coordinate of our point. The approximation for f of 2.6 is 1.92 plus 0.7 times 2.6 minus 2.8. That is 1.92 plus 0.7 times negative 0.2 0.7 times 0.2, well 7 times 2 is 14, and we need 2 decimal places, so 0.14. And then we need to subtract 1.92 minus 0.14. That's 8, we borrowed 1, so 7, 1.78, so 1.78. That is our approximation for f of 2.6 using Euler's method with 2 equal steps. Alrighty? Okay, now I added this problem. So if you're watching in 2025, this is a new problem. So if you want to write it down, write it down. If you want to just enjoy the show, enjoy the show. Alright? Okay. I wanted to give you one problem with words, well, a story behind it, because I have seen AP do this very recently. So I think that this is how they might be testing Euler's method from here on out. I took a situation, I changed a little bit of an old AP question, FRQ. I took the background for it, but then I changed it a little bit to suit this Euler's method question. Alrighty, at time 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees at time 0. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies this differential equation, where h of t is measured in degrees Celsius and h of 0 is 91. Use Euler's method with 2 steps of equal size beginning at time 0 to approximate the internal temperature of the potato at time 10 minutes. This one I'm going to treat like an FRQ. Okay, so I want to show you what you could do for an FRQ version of a problem. Okay, I'm going to start out like we've been starting out. I like to write my point, my initial point, and my initial point is 0, 91. Now there's a story behind this. So 0 is not just an x-coordinate, this is my time, and 91 is my temperature, h, right? We're going to take 2 steps. And we're going to end at time 10. So we're ending at time 10. This temperature will be my answer. We are approximating that temperature. So my middle time is halfway between 0 and 10, 5 minutes. Okay? So I will get my y-coordinate at my middle point and then use that point to get my answer. Point and slope, and then EQ. Point and slope, then EQ, then approximation. My first point is 0, 91. Perfect. My slope is given to me right here. This is my slope equation. Of course it's not dy dx because we don't have y's and x's. We have h's and t's. So instead of dy dx, it is dh dt. So I see that my slope equation is only in terms of h. So I will be using only the 91 over there. So my first slope is negative 1 over 16 times 91 minus 27. This is an FRQ, so I'm not going to deal with this. I'm going to call this something that I can move forward with. I'm going to call that A. So instead of subtracting and then multiplying, I'm not going to do it. I'm just going to call it A and use A. Therefore, my equation will be y minus the y-coordinate of our point is equal to the slope times x minus the x-coordinate of our point. My approximation is, we don't have an f, we have an h here. H at 5 is approximately equal to I add the 91 over a times 5 minus 0. And again, I don't have to figure this out. I can call that b. So h of 5 is b, right there. And now we go and use that point in our second step. So point and slope, and then EQ. And lastly, approximation. The new point is the point 5b. The new slope will be negative 1/16 times the h coordinate, which is b, minus 27. So the slope is negative 1 over 16, b minus 27. And you can probably guess what I'm going to call that. I'm going to call that c. So my equation will be y minus the y coordinate of our point is equal to the slope times x minus the x coordinate of our point. Our approximation will be for h of 10. So I'm going to solve this for y and put 10 in for x. Add b to the other side, put 10 in for x, and we are done. FRQ, we are done. We have said what the approximation for h of 10 is. We stop. Okay? If it hurts you a little bit to do that, you can say that this is equal to d and put d up here. But I wouldn't. I would just stop right there. Alrighty? So guys, this is Euler's method. It's a numerical method for approximating a value of a function. If you are given one value of a function and a way to find slope. Alrighty, hopefully that all made sense. And you enjoy it. So Euler's method to me is very predictable. Very predictable. It's very organized. You always do the same thing each time. Now, you may be wondering, in all four of these examples, we only used 2 steps, didn't we? Of course, you could have more steps. And to get from 0 to 10, if you wanted a very, very accurate answer, you would use more than 1 step, or more than 2 steps to get there, okay? For College Board, they want you to know the process. And what I have observed on College Board with their questions is that they like 2 steps. 2 steps is enough to let them know if you know the process. So you can expect 2 steps on the AP exam, and you can expect 2 steps on my work as well. All right, that's it.